Okay, so we'll start with an example. So suppose we have a set of items and you have a set of agents, and we want to match these items to these agents. And each agent has a value for each item. So what would you normally do? You would just compute a maximum weight matching in this graph. However, the input to this problem, which is the weight on the edges, come from the agents, which is their valuation for each item. And therefore, if they were strategic, they could possibly misreport their valuations, and we wouldn't get the desired outcome. So a mechanism is just an algorithm which takes into account the incentives of the agents. It tries to, well, the outcome of the mechanism is measured, the performance of the mechanism is measured with respect to the true input and not with respect to the reported input. In this case, for the maximum weighted matching algorithm, there is a way to come up with a payment scheme to make it convert it to a truthful algorithm, which means everyone would report their true valuation for the items. Okay, so here is a bit of terminology. For each agent I, we denote the private information of the agent, which in this case is the valuation of agent, by her type, which for agent I it's denoted by little ti. A capital Ti is the type space of the agent. And for example, the agent, in this case, we can have discrete types or continuous type space. In a discrete type space, we have a bunch of types like A and B, for example, and then we can define information, other information of the agent space for each type separately. Like, for example, type A has a valuation vector 5, 3, and 2 for the 3 items. And continuous types, an example of which is, for example, if you have R cube, where the valuation of each component of the vector is the valuation of the agent for each of the items. And each agent has a utility function which basically maps the types of the agent and outcomes to real value numbers. The utility function basically compares the different outcomes for the agent and ranks them in order of preference. For example, in this case, a utility function might be the valuation of the agent for the item based on its type multiplied by the allocation minus the payment. And we denote the profile of type by a vector consisting of the types of all the agents. And we use capital T to denote the type space of all the agents together. So a mechanism is basically a mapping from type profiles to outcomes. So in this case, an outcome could be an allocation and a payment. The deterministic mechanism is just a deterministic mapping from type profiles to outcomes, whereas a randomized mechanism maps each type profile to a distribution over outcome. For most of this talk, we consider randomized mechanism. So here is a popular mechanism called the Vickrey-Clark-Groves mechanism. It computes the socially optimal outcome. Basically, if you have any algorithm that can compute an optimal social optimal outcome, you can convert it to a truthful mechanism by setting up a payment scheme where VCG tells you how to set up the payment scheme. And it's basically the payment of each agent is his or her externality on the other agent. Basically, how much he reduces the utility of the other agent by entering the system. And it's truthful. Basically, every agent reports their type truthfully, this mechanism. But it has a number of limitations. So basically, you have to be able to compute the optimal allocation. If you can compute an approximation, it breaks. It doesn't give the truthful mechanism. It requires quasi-linear utilities, which means your utility function as a function of your type allocation and payment should be, you should be able to write it as a function of your type and allocation minus the payment. So the payment should be an additive term. And it only works for maximizing welfare. You cannot use it to maximize other objectives like revenue. So here is a bit of more definition. So not all mechanisms use money, but mechanisms that use money, just as I defined in the previous slide, if the utility function can be written of this form, it's called quasi-linear. Otherwise, if it is just some arbitrary function which is decreasing in payment, it's called non-quasi-linear. For example, if you have budget constraint, and your utility goes to minus infinity if your payment is above your budget, you have a non-quasi-linear utility.
The employee prime has some if in it. If xi is equal to 0, then the payment should be 0.
No. I mean, it's just your utility function. It doesn't tell you what the mechanism's outcome is. For whatever outcome you get from the mechanism,
you just plug it in. You usually have it. If you don't get anything, then it should be 0. Otherwise, that is...
No, it doesn't have to.
Not have to, but usually it is the case.
I mean, that depends on what your mechanism is. Your utility function is independent of the mechanism. If I just give you, I don't give you anything, but I take $2 from you, your utility is going to be negative 2.
Just give him a counterexample. What would be a mechanism that doesn't satisfy his condition, but is perfectly fine in your framework?
Well, if you have a all-pay mechanism, or all-pay option, for example, you may not get anything, but you have to pay anyway. Okay, so for an example of mechanism without money, for example, there are mechanisms where payment may be inappropriate, like if you have a residence hospital matching or voting, other examples. And we consider truthful mechanisms mostly where the reporting of type is the best strategy. And you can classify mechanisms based on the prior free, like ECG or Bayesian mechanism. So a Bayesian mechanism basically assumes a distribution on the types of the agent. So for each type Ti of the agent, we assume that Fi of Ti is the probability of type Ti. And for most of this stuff, we assume types, agent types are distributed independently. So basically, this capital F is a product distribution. Sorry, the old F capital. And for whatever objective we are optimizing, we consider optimizing the objective in expectation, not at every instance. And in Bayesian mechanism design, we often consider Bayesian incentive compatibility as opposed to the dominant strategy, which means you are truthful assuming where you can maximize your utility in expectation where the expectation is taken over the types of other agents. But in dominant strategy, you assume that you maximize your utility, but truthful reporting, assuming that even you know the types of other agents. So this is a little bit less restrictive. Okay, so my talk has 3 parts. The last part is conclusion, technically, it's not part. The first part is Bayesian mechanism design, the second part is prior free. So most of my talk will be the first part. Okay. So for Bayesian mechanisms, we define 3 allocation rules, ex post, interim, and ex ante allocation. So basically, the ex post allocation rule is almost the same as the mechanism itself, minus the payment and some other attributes. It tells you for each profile of types, what is the allocation for each agent. And it could be like a distribution of our allocations. So I'm just loading the notation here. An interim allocation rule tells you the expected allocation of each type where the expectation is taken over the types of the other agent. I will explain this with an example in the next slide. And an ex ante allocation rule specifies the ex ante expected allocation of each agent, which means before you see the type of the agent, over all possible types of that agent, what is the appropriate expected allocation? So here is an example. Suppose you have 2 agents, and they have these 3 types. The first agent has these 3 types, A, B, and C. The second agent has types D, E, and G. And let's say you want to allocate this item to the agent with the maximum valuations. Basically, consider the welfare maximizing allocation. So let's say the first A and B have valuation of $3, B and E $2, and C and G $1. And all types, let's say, have equal probability. So the ex post allocation rule is basically like a table which says, for example, if type A and D show up, then the first agent gets the item with probability of 1/2, the second also gets with 1/2. And you can see that A wins against E and G, basically gets the item with probability 1 because the valuation of A is higher than E and G. And so basically this, the size of the ex post allocation is proportional to the product of the sizes of the type spaces of the agent. So basically this ex post allocation grows exponentially in the number of agents. the interim allocation rule basically has an entry which specifies the expected allocation of each type. So we have aggregated all the types of all agents in one vector. And it's also normalized by the probability of each type. So for example, this agent, this type A, wins with, so each of these columns happen with probability 1/3. So it's total here, it's 2.5 over third, and you have to also normalize it by 1/3, which is the probability of this type, which is, you get 2.5 over 9th, which is 5 over 18. And the ex-ante allocation rule, as you can see, it's very small. It's actually proportional. Its size is proportional to the number of items times the number of agents.
So how do you compute the ex-ante?
This is the expected allocation of this agent. So basically, you just add up these three. So these three types of the agent one, because they are already normalized by the distribution.
But they add up to half, not one. So
yeah, they add up to half. Sorry.
Okay.
Yeah, you add these three. Well, you're basically normalizing each one by the probability of each type. So I mean, these three won't add up to one unless the agent is always getting the item. Yeah, so because the two are symmetric, it's obvious that each one should get the item with probability 1/2 in expectation if you don't know the types. All right. So
but hold on. But what is the probability distribution over the type of agent?
Yeah, I assume that all types have equal.
Oh, equal.
Yeah. Otherwise, this wouldn't be these numbers. Okay. So basically, the main result of the first part of my talk is that we present a computational efficient framework for reducing the mechanism design problem for multi-agent to single-agent problems, which works in a very general setting. And we make these assumptions. So these are the basic assumptions. There are some minor other assumptions that I will tell later. So we assume that agent types are distributed independently. We assume that the objective, whatever objective you want to optimize, is linearly separable over the agents. For example, if you're maximizing revenue, that's the sum of the revenue you get from the agent. So it's linearly separable over the agent. And we assume that there are no inter-agent constraints except for allocation constraints. But we can have arbitrary combinatorial constraints on the allocation. Okay. So the idea is the following. If you have a multi-agent mechanism, it basically induces a single-agent mechanism on each agent, which you can get by basically, if you have, like, this is a 3-agent mechanism, if you simulate these 2 agents, and this agent, because their types are independent, this agent will not be able to tell whether the mechanism is actually being run by simulating this other 2 agents or whether there are actual other agents. So if you simulate these 2 agents, what you have is actually a single-agent mechanism, which, because the simulated agents are just part of the mechanism. So this way you can convert every multi-agent mechanism to single-agent mechanism. So the idea is to optimize over single-agent mechanism for each agent and then combine them back to a multi-agent mechanism. But this could be, this would lead to an infeasible mechanism if we just do it naively, because the allocations are not, the allocation constraints couple the allocations for this single agent. So we can't just do it by that. So the approach that we use is to optimize the single agent mechanism simultaneously subject to like a relaxation of the joint feasibility constraint, and then we combine them back. Okay, so the first part of my talks basically has 3 sections. The first one I explain the composition, the multi-agent single-agent composition using the interim allocation rule. The second one is using ex-ante allocation rule, and at the end I will talk about some applications to outside of mechanism design. So the first part is a joint work with Lu Fu, Nima Hackman, Jason Hartline, and Azar Shmeleki. Okay, so we will use this notation here for a vector like types. We will write types indexed by some, subscripted by some index minus I to denote the vector that results from removing that index. Basically, we have removed Ti from this vector. Okay, so let's say we have a single item and we have budget constraint agents, and we want to design a mechanism that maximizes revenue. So here is a linear program that basically computes the mechanism for us. So we are not going to actually use this linear program. It's just for the sake of explaining how things can be done. So this linear program has basically three sets of variables: the interim allocation rule, the ex ante allocation rule, basically the ex ante allocation rule, and the payment variables. So the objective basically maximizes the expected payments over all the agent types. And this is the incentive compatibility constraint. On the left side, you have the utility of agent I with type TI. This is basically the valuation of the agent. This is the allocation of the agent when reporting type TI, and this is the payment when reporting type TI. And on the other side, this is the utility for the same agent when his type is still TI, but he is lying about his type, and he's reporting T prime. And basically, this constraint ensures that there is nothing to gain by lying, because this is less than or equal to this. The second set of constraint, this is the individual rationality. This tells you basically your utility for any type should not be negative. And this is the budget constraint. It says for every type, your utility your payment should not be more than your budget. And then this red constraints here, this is the ex post allocation constraint. It tells you the total allocation of the item for the agent for each type profile should not be more than 1. And this constraint basically relates your ex post allocation rule to your interim allocation rule. Basically, the right-hand side is taking the expectation of the allocation of agent I over the profile of types for the other n-1 agents.
Can you explain the FI-TI one more time?
Fi is the probability of agent I having type TI FI-TI. So that is the expected revenue. So if you look at this linear program, the thing that is obvious is that this blue part of the linear program, the size of it is proportional to the total number of types of all the agents. However, this part, the size of this part is exponential in the number of agents because it's basically using the ex post allocation rule. And if you notice that this is the only part that's dependent on the ex post allocation. The whole part, the whole rest of the linear program only requires the interim allocation rule to compute. So let's talk about feasibility of interim allocation rule a little bit. So we say an ex post allocation rule, an interim allocation rule X tilde is implemented by an ex post allocation rule X triangle if they satisfy this inequality. So basically, this is taking the expectation over the types of other agents. And we denote the space of feasible interim. Okay, so we say an interim allocation rule is feasible if it can be implemented by some feasible ex post allocation. And we denote the space of feasible interim allocation rule by capital X tilde. It's easy to show that this capital X tilde is always convex for itself, regardless of whatever combinatorial allocation constraints you have, assuming that you allow for randomized mechanism. Okay, so here is how we define the single agent problem. Given an interim allocation rule X tilde, we want to compute the optimal mechanism for agent I subject to the interim allocation rule being X tilde sub I. And we also want to compute the expected performance of the mechanism. So for example, if it's revenue, we want to compute the expected revenue of the single agent mechanism subject to that interim allocation. And if that interim allocation rule is infeasible, Ri can be negative infinity. That's fine.
So what do you mean by subject to? You are assuming that we have this interim rule?
Yes, suppose I give you the interim allocation, I tell you I want the expectation of the expected allocation for each type should be these values that I'm giving you. And
the output should satisfy this problem.
Yeah. And suppose I'm giving you this, and I am asking you to compute like the other things, like the payment, and maybe there are some other attributes that your mechanism has to compute. So what we show is that this Ri function is always concave in X, regardless of your allocation constraint. And like for any setting, this function is always concave. And the thing is that we can compute the optimal interim allocation rule by solving this convex program. So this constraint forces your interim allocation rule to be feasible, and basically you're just maximizing the sum of the performances of the single agent mechanisms that we have. So let's go back to the linear program that we had before. So if you remember, this was the part that involved the ex post allocation rule. So, and if you look at the top part is actually decomposable over the agent, because for each agent I, these constraints are totally separate, and the objective function can also be separated. So basically, the single agent problem can be solved by this other linear program. where if you have already given me the interim allocation rule x tilde, all I need to compute for this case is just the payment. So the only variable in this linear program is the pi. And as you can see, the size of this linear program is just proportional to the size of the type space for the agent.
So in the second line of equations, the fi is a ti, not a ti prime.
Oh, this one should be ti prime. Yeah, you're right. Sorry. Yeah, because this is your allocation subject to reporting t prime I. So that should be prime. Okay, so the single agent problem is the size is considerably smaller because it's proportional to the type space of the single agent. So now the questions that we need to answer in order to be able to use this approach is the following. First of all, how we can we optimize the interim allocation rule over this? Because this is the space that we don't know how to, we need to be able to basically optimize over this space. And the second question is, if I give you an interim allocation rule, how can you come up with an ex post allocation rule that implements it? Okay, so before going further, I want to define how we represent the allocation vector. So, for example, suppose we have a matching problem, and each agent has 3 types, and suppose this is the profile of types that we reported. The first agent is A, and the second agent is type E. And let's say there is an outcome in which, you have a mechanism that computed an outcome in which agent 1 gets item 1 and agent 2 gets item 2. So normally you would represent the outcome by this allocation vector, which has like an entry for each agent and each item. So agent 1 gets item 1 and agent 2 gets item 2. But instead of representing the allocation vectors in this way, we will use a flattened version of the allocation vector, which has an entry for each type of each agent. And for example, when this type is reported, all of the types that are not in the type profile, their allocation has to be 0 because they haven't showed up. And you can see that only agents type A and type E have non-zero allocation. Now the nice thing about this representation is that, and we also define the space of feasible allocation, flattened allocation under type profile T by X, capital X sub T.
Can you define it again? So how do you represent it again?
But instead of this little vector, I can just make this vector redundant. I would put one entry for each type of each agent. And under each type profile, I basically specify the allocation for a specified. For example, if the type profile defaulted is A and E, and agent 1 gets the item, then for this entry which corresponds to type A, I put 1 because the agent 1 type A is getting item 1, and type E of agent 2 is getting item 2. So there is a 1 here. That specifies the allocation like that. So the nice thing about this representation is that if you take the expectation of this allocation vector, the flattened allocation vector, you get the interim allocation. Because basically this one specifies the allocation for each type independently. So when you take the expectation over all types, you know the expected allocation of each type. And this is a critical thing for the way we compute basically we solve the problem.
So one question, in this setting, do you have the original payoff matrices, or you want to compute also that one?
No, we don't have any of the matrices.
So you have only interim, essentially.
I don't have, okay, so I don't have the interim ex post horizontal allocation. I was just explain the relationship between them. That is what I want to compute. Basically, I want to use this convex program to compute the optimal interim allocation. But the thing is that this is a polytope which is, we don't know how to represent this polytope, the polytope of interim allocation.
You don't know, it's like the original payoff matrices, like the one that we are creating. That n times m things for the...
No, we don't have the ex post allocation rule. We just have the interim allocation. So, as I said, there are 2 questions that we have to answer to use it. So first of all, we have to be able to solve this. And once we have solved it, to be able to construct a mechanism, we have to come up with an ex post allocation rule that implements it. Basically, we have to consider, basically compute that matrix thing. But we don't explicitly compute that matrix thing. So we only need to compute it for the current profile of types. Like you see the profile of types and you compute the exposed allocation with just that profile. Because if you want to compute the whole exposed allocation, it's super exponential in number of types. Okay, so let's go back.
So you're saying that flattened allocation vector is all conditional on the actual realization?
This is the condition on the actual profile of type that is reported. So assuming that T is the reported profile of type, the only feasible allocation vectors would be if this only these two could be non-zero and only these two could be non-zero if the profile, for example, is A. And the other one has to be zero under that type profile.
Okay.
So basically for every profile of type, your allocation space X sub T is just some polytope. And if this is a random polytope, this is a stochastic polytope because it depends on your type profile. And what we want to do is basically, if you have an interim allocation which is represented by this X tilde, this can be implemented if we can choose a point like X from each of these polytopes, such that in expectation we get this one. And basically the space of all physical interim allocation will look something like this, where for every point X tilde, there is a way to come up with, like, select something from each of those polytopes to get that point in expectation.
And do we know it is convex?
It is it's easy to show that it is convex. Because basically, if you have two interim allocation rules, any convex combination of them is an interim allocation because you can randomize each one of them. Like if you can implement each one separately and then randomize between the implementation and you get whatever is the expectation of that. Okay. So now we want to solve an optimization and implementation problem over that polytope. So let's see. So the first step, I show that it's easy to compute to optimize a linear objective over the space of feasible interim allocation. If you have a linear objective, basically what you want to do is you want to go as far as possible in this direction. So basically this is, for example, the optimal in this direction. If you take the image along this vector, it has the biggest image. So it turns out that if you want to optimize along some direction, you better optimize along that direction in every realization of this stochastic polytope. In fact, if you take the optimal vertex which goes in this direction and take the expectation of this X, you get exactly this vertex. And the nice thing is that you don't actually need to consider all possible realization. You can actually sample from this polytope and then take a bunch of, like, optimize along this direction, take a bunch of these X's and then take the average of them, and you can compute this with high probability by sampling.
And you know the precise relationship between the error and the sample size?
Yeah, you can just use Chernoff time, because this is just a random variable. You just repeat, and you get as close as you want to the actual point. So this tells you that you can basically optimize in each direction without actually knowing how that polytope looks like. Another implication of this is the following: if you take any vertex of this polytope and you find a separating hyperplane going through that vertex, if you take the normal vector to that vector which is normal to that plane, and then you can implement this vector by simply optimizing along the normal vector over every instance of this polytope. So basically, we have answered the following two questions. For every linear objective, we can optimize over that polytope, and every vertex of that polytope we know how to implement. We know how to compute the exposed allocation rule, basically. So, so basically, but we don't know what the polytope looks like. Basically, if we optimize, we find some point, and all we know is that the polytope cannot be to the other side of this, to the other side of the separating hyperplane, which is orthogonal to that direction. So the question that we need to answer now is, how can we actually optimize the concave function? Because that is what we want to do. We don't want to just optimize linear function. And then how can we implement a non-vertex? So the short answer is we're going to use the ellipsoid method. So here is just a 2-minute introduction to the ellipsoid method. So let's say it's basically a binary search in higher dimension. So let's say there is a point you want to find, and you don't know where it is, but if I give you a query point, then you can find a plane that cuts the space in half and can tell you which direction you have to go, like which side of the plane your target is. What the ellipsoid method does, it's basically very similar to the binary search. At every step, it queries a point, and you're supposed to find a separating hyperplane which cuts the space. And it continues like this, and after a while, this space of possible points gets smaller. Except that the ellipsoid method, instead of keeping track of this polytope, it just uses an ellipsoid. And the ellipsoid has some redundancies. It just includes this orange part, but that is fine. And at every step, the ellipsoid method queries the middle of the ellipsoid, and you're supposed to find a hyperplane which tells you which side your target is, and then it will shrink the ellipsoid, and it will eventually converge to that point. So in order to use the ellipsoid method to find something, you have to be able to find the separating hyperplane at each step. So to optimize the concave function, we use the ellipsoid method in the following way. Whenever a point is queried, if it is outside the visible space, we find a separating hyperplane which tells us which side the polytope is. And if it is inside the polytope, we just find a separating hyperplane which is normal to the gradient of the concave function. So let's assume that these green lines are the gradients of your concave function. Okay, so now suppose
Is this also how the convex solvers work in practice? Or?
No, this is actually only for theoretical.
Yeah.
No, I know that, but I was wondering, like the convex solvers, do they use any of these ideas?
I think they use interior point method. Okay, so now let's say we want to compute the separation oracle for this space of visible interim allocation. So basically, we want to come up with a line which looks like the plan. So instead of looking for the separating hyperplane itself, we will look for the normal to the vector which is normal to the separating hyperplane. And the nice thing about the normal vector is that we can verify whether it creates a separating hyperplane or not. Because if you have already given me that, okay, so basically there could be multiple separating hyperplanes. Basically, if you take any of those green lines, that gives you a separating hyperplane. And the nice thing about the looking for the normal vector instead of the plane itself is that you can verify it very easily. So if you tell me that green vector, I can just optimize along that vector. And now if that red dot basically has a bigger image along this vector than the black dot, you know that it's a separating hyperplane. And you already know how to optimize a linear function. So this is easy to do. Basically, even when you don't know the polytope, we can always do this. So we are going to use this idea to actually to find the normal vector. And to find the normal vector, we are actually going to use the ellipsoid method itself. So it's like a nested ellipsoid method, where each call to the separation oracle itself runs another copy of the ellipsoid method. So let's say the higher level ellipsoid method has queried that red point. And now we want to find a separating hyperplane for that red point. So we run another ellipsoid method to find the normal vector. So let's say the second level ellipsoid method has queried that green point. We optimize along that direction. Let's say we found this black. And now we look at the images of this black and the red dot along this line. So the black dot has a bigger image than the red dot. So this doesn't give us a separating hyperplane for the red dot. However, if you connect the black and the red dot, it actually gives us a separating hyperplane for the normal vector. So we can cut out all possible normal vectors in this direction, because if you try any of those normal vectors, they're not going to give you a separating hyperplane, because for all of them, the image of the black dot is going to be bigger than the image of the red dot. So now we have cut half of the space of normal vectors. Again, the ellipsoid method queries another normal vector. We find another point, and it's not a separating hyperplane for the red one. So we again cut that green space, part of that green space. And now the third time, let's say the ellipsoid method queried that green line. We optimize along that direction. We find this black dot, And now the image of the red dot is bigger than the image of the black dot, so the red dot cannot be part of our original space of interim allocation. Basically, anything on the other side, like in this orange area, cannot be inside the polyset. So the idea is that, like, in short, we are basically doing the following. In the nested call to the ellipsoid method, if every time that a green vector is queried, if the image of the green dot, basically the red dot, is smaller than the image of the green dot, we find a separating hyperplane for the normal vector. Otherwise, we find a separating hyperplane for the query points. Okay, so we solved the separation problem over the space of physical allocation. Now we can optimize the interim allocation, concave functions over interim allocation. So now we want to answer implementation question. So we already know how to implement vertices of this polytope, but if we have a point inside, we want to see how we can implement it. So the idea is the following. We can randomly select a vertex of this polytope such that in expectation we get this, and then implement one of the vertices. So here is how we do this. We basically round this point to a vertex such that in expectation we get this point. So pick any direction. Let's say this distance is alpha and this distance is beta. At the first step iteration of the rounding, we pick one of these 2 points, which I call x1, at random with these probabilities. And you can see that in expectation, you get your original point. So let's say we pick this one. And then at the next step, again, you do the same thing. And you get a vertex. And now you have a vertex, you know how to implement a vertex. And because your vertex is in expectation the same as your original point.
And what do you mean how can implement a vertex?
Okay, so what I mean by implementing a vertex is that if you see a profile of types you want to compute, well, first of all, you don't need to compute the exposed allocation rules for all possible instances. It's went out of focus. So you don't need to compute the exposed allocation rules for all possible type profiles. Basically, what you want to do is that if I give you a type profile, you want to, I'm asking you to give me an allocation which is drawn from the distribution specified by the exposed allocation rule. And to draw an allocation from that distribution, what you can do is the following. You take this interim allocation rule, you round it to a vertex, and then for a vertex, you know how to implement. You just take the vector which is normal to the separating hyperplane and optimize along that vector over each realization of your space. Okay, so that was how we can optimize over general polytopes, but it's not very efficient because it uses ellipsoid method at 2 levels. So now we show that it's actually for a large class of problems, the space of allocation rules is specified by a polymetric. So I'm going to define this formally by an example. So suppose we have 1 item and 2 agents with these types, and the possible allocations. So this is basically how your flattened allocation vector looks like. So observe that in this case, the only allocations that are possible, if that is the reported profile of type, is that A is 1 and everything else is 0, or E is 1 and everything else is 0. So if you look at it carefully, basically you can see that you can specify your allocation constraint by a set of constraints of this form. Basically, for each subset of types, this is for this particular example. For each subset of types, the sum of the allocations of those types have to be less than this quantity. So, for example, if there is a type which, if S is a singleton containing a type which is not in the type profile, then this side is 0, which means the allocation for that type should be 0. Otherwise, for example, if S contains multiple types that appear in the type vector, this part is at most 1, so which means you can allocate to at most 1 agent.
You don't need every possible subset, do you? Or do you need, like, what do you need the subset ABC, for example, or is that redundant?
What do you mean ABC? But that's redundant. Yeah, of course that's redundant. But so I'll tell you why this is important, because this is actually a polymetric specification. So if you have an allocation, a set of combinatorial constraints on the allocation, where you can specify it of this form where f sub t of s is some submodular function. This specifies a polymetroid. And it has several nice properties, which I'm going to explain. So first of all, if you take the expectation of both sides, on the left, this becomes the interim allocation, and this part becomes the expectation of this submodular function. Now, if you have a submodular function, okay, so basically this condition is necessary for the feasibility of interim allocation rule, of course, because we just took the expectation. But now it turns out this condition is also sufficient for feasibility of interim allocation rule. And another implication is that the space of feasible interim allocation rule itself is a polymetroid, because if you take the expectation of a bunch of submodular functions, it's going to be another submodular function. And the important implications of this polymetroidal characterization is that optimizing over polymetroid is much easier than general polytopes. So here are a couple of examples of problems where you might have a polymetroidal constraint. So let's say you have a network of nodes and you want to construct the network by like a spanning tree in this network, and the edges are owned by some agents, and possibly an agent may own multiple edges. So the set of all the spanning trees is a matroid, which can be represented by a polymetroid. And here is another example. Let's say there's a set of agents, and you want to select a subset of them to receive some service. And you want to select at most 10 agents, but from each subset you want, from females you want to select no more than 6, and also from males you want to select no more than 6. And this is a laminar set of constraints. Basically, if you have any laminar set of constraints, you can also represent it by polymetry. So here is a bit of related work. So this polymetroidal, basically this condition for feasibility and sufficiency of interim allocation rule for the case of single item, it was discovered, the necessity of that condition was discovered by Matthews and Maskin and Riley independently. And well, if you look at this condition, it's actually the same as this condition that I showed you a couple of slides ago, but it's written in slightly different notation. So by looking at this, it's not obvious that it's a polymetroid, whereas in this case, it's clear that it's a polymetroid. And the sufficiency of that condition, again, for the case of single item with no combinatorial constraints, that was proved by Border. And here are a couple of other related works. So basically, Meyerson gave analytical solution for optimal options for a single item. And this paper here, Fai et al., which is a recent paper, they independently developed similar techniques for additive evaluations where the only combinatorial constraints are slice space. You cannot use this continuous type space have infinity many times. So we are going to use the ex-ante allocation. Remember that the ex-ante allocation rule just specifies the expected allocation of each natural constraint, like matrix constraints or anything, just simple supply constraints. And we assume that each agent demands at most 1 unit of each. And this assumption is not necessary. This is just for the sake of exposition. So it's obvious that this condition is necessary for a feasibility of ex-ante allocation rule, because the sum of the expected allocations of all the agents for each type should not be more than the supply of that type. For each item should not be more than the supply of that item. But this is not always sufficient. So here is an example. Let's say you have n agents, and each agent has 2 possible types, high and low. And the high type shows up with probability 1n, and otherwise it's low type. And the high types, the ex-ante allocation rule is 1 over n. So basically, it means whenever the high type shows up, it has to receive the item. But it has to be 1 over n. And as you can see, the sum of the ex-ante allocation rules add up to exactly 1. So this constraint is satisfied. However, there is no way to come up with a feasible implementation of this, because what if two agents show up with high type? You cannot allocate to both of them with probability 1. So we have to compromise some. So here is how we do the decomposition. This is very similar to interim decomposition with some slight difference. So the main idea is that so the single agent problem is defined as follows. If I give you an upper bound on the ex-ante allocation rule, you're supposed to compute a single agent mechanism subject to that upper bound, and also compute the optimal performance of the mechanism subject to that upper bound. And again, we show that these ROI functions are always concave regardless of the specific problem you're looking at. And you can use this convex program to compute some kind of optimal upper bound on the exam allocation rule. But the optimal value of this program also gives you an upper bound on the optimal value of the expected performance of the optimal mechanism, basically. But this is only an upper bound because it may not be a feasible mechanism. It could basically, what you're computing may not correspond to a feasible mechanism. So what we are going to do, because there may be no feasible implementation for an horizontal allocation, we are going to approximate the implementation. We'll come up with an approximate implementation. So here is a general approach that we use. We start by solving this convex program, and let mi of x bar subject to x bar I be the optimal mechanism subject to that upper bound. We are going to run these single agent mechanisms independently, and then we are going to resolve the conflicts. Because if you run this independently, each supply constraint will be satisfied in expectation. But it could be that there are in some instances you are over allocating the items. So we will resolve the conflicts by somehow doing the unallocating items or some other way. So this is the step where we lose on the performance. However, we try to minimize that loss. So the way we resolve the conflicts by reduction to the magician's problem, which I'm going to define. So this is something that I have made up. It's not a well-known problem. So here is the problem. So there's a sequence of boxes that arrive online and they're presented to a magician. There might be some prizes in some of the boxes. And the magician has K magic wands, and he can use a wand to open a box and get the prize if there's any prize. However, if he opens a box, his wand may break with a probability which is written on the box for box I will be denoted by x sub I. And it's given that the sum of the x sub I is less than or equal to the total number of wands. So if he tries to open all of the boxes, in expectation he should have enough wand. But if he does that, the probability of having a wand when he gets to the last box is actually could be arbitrarily close to 0. Okay, and alternatively, he could skip the box. Now, in order for the magician to get the prizes to maximize his utility, whatever that could be, he has to try to simultaneously maximize the probability of opening every box. And we assume that everything has been arranged by an adversary who doesn't, and we assume that the magician has no prior information except for the number of wands. And we present a solution. I don't explain the detail of the solution, but we present an algorithm which guarantees that the magician can open with each box with at least this probability, 1 minus 1 over a square root of k plus 3. So for the case of k equal to 1, where the magician has 1, this is at least 1/2. And as k goes to infinity, this approaches 1. So I'm going to use the magician problem, the solution to the magician problem, to develop basically multi-agent mechanics. So I will start with an example. So let's say you have a single item, but you have k units, and you want to maximize welfare, and you have n unit demand agents, each one having a valuation VI drawn from some distribution, capital Fi, where the distributions are known. Of course, you can solve this easily by just an auction, like a second price auction. But there is some other reasons you may not want to do that. I will explain the reasons later. Okay, so for each agent I, subject to an upper bound on the probability of allocation, the best thing that you can do to maximize the welfare of that agent is to find a price such that the probability that the agent's value is above that price is exactly equal to this probability, and then you just sell to the agent at that price. And the probability that you sell is just this exactly. And you can compute the expected performance of the single agent mechanism subject to this should be x bar. It's exactly this integral. Basically, you're integrating from this price up to infinity the valuation of the agent weighted by the distribution of that agent. So here is how we use this. We solve basically that convex program which consists of this, and then we create a box for each agent, and on each box we write this X bar I, basically on the box for agent I, and we present those boxes to the magician. And if a magician opens the box, then we offer the item to the corresponding agent at price PI. Otherwise, we do not offer the item to the agent. And if an agent buys the item, we break the wand of the magician. So the wand will be broken with probability, with this probability. That is the probability of agent being above the having valuation above the price. And this is by using the solution to the magician's problem, you can basically get this fraction of the optimal social welfare, because you are basically offering the item to each agent with at least this probability. Now, the nice thing about this mechanism is that it's actually an online mechanism that may serve the agents in arbitrary order. So you don't have to, like in a regular auction, you have to have all the agents at one place. But let's say the agents arrive one by one, and you have to decide at the time they arrive. You cannot wait until they are all there. And it gives you basically a way to handle that. And it generalizes profit inequalities. Profit inequalities is basically a different problem. Basically the same problem with a different statement where k is equal to 1. You have 1, 1. So here is the general idea of how we implement basically the multi-agent mechanism by approximately implement the ex-ante allocation. The idea is similar to what we did in the previous slide. We create m magicians, one for each item type, and then we run the single agent mechanism. So we present two approaches, pre-running and post-running. I'm explaining the first one. So in the pre-running, then we run the single agent mechanism sequentially, and we use the magicians ensure that each item is offered to each agent with at least this probability, assuming that there is at least k units of each item. And then we show that basically you get this fraction of the optimal objective, whether it's welfare, revenue, or whatever. But there are some technical assumptions.
Can you give some intuition as to why that is the natural function that you get? And why does it depend on square root k, for example? Does that mean?
Well, this is actually like a section of my paper. So I don't.
But there's no intuition specific to why. You just optimize the parameters, and that's what you get.
Well, it's not optimizing parameters. So I don't know how. Let's explain after that.
Okay.
As long as it's interrupted anyway, just so that I really understand this problem. Is another way of looking at this, you're selling identical units, you could just do it with a simultaneous auction, and you can figure out what the distribution would be as a clearing price, but what you want to do instead is just offer it to agents at a posted price one by one, and is the problem basically how close you can get to the optimal solution, doing it one at a time with a posted price?
That was the thing with this example that I showed here, but where is the example? But the problem is, this was just for the sake of presentation, but if you have multiple items, then, and let's say you want to maximize your revenue, then, like, if you have a single item, you can use the Myerson's optimization. If you have multiple items, there's no way to do that, basically. Like, I mean, there's no analytical solution except for very special cases. And if you want to compute it, like using any linear program or something, it's going to be exponential in size. But using this ex-ante decomposition, you can actually decompose the problem over the agent and then use something similar to the magician technique, except you use it for multiple items instead of single item. And that is the point of using this. For single item, of course, you can always just run a simple auction. So this is actually for multiple items, because we use m magicians, one for each item. And okay, so another approach is post-rounding. We basically, again, have one magician per item. But we run all the single agent mechanisms simultaneously, and then we go unallocate some of the over-allocated items and adjust the payments accordingly. And again, we show that each allocation will be preserved with at least this probability. And there are some other technical assumptions which I'm not mentioning. But given those technical assumptions, you can preserve this fraction of your objective. Okay. And if you cannot compute the optimal single agent mechanism, but you can compute that Ri is an upper bound on the optimal, and you can obtain an alpha fraction of the upper bound, but your final multi-agent mechanism is going to do like your approximation factor just carries over to your final multi-agent mechanism. And here is just a short list of mechanisms that the approximation factors that we obtain using this framework. These are the previous best known approximation factors, and these are the current ones. And you can see that we can improve most of them, like all of them, but by different degrees. And for this last one, the first three assume continuous type spaces, so we couldn't use the interim allocation decomposition. But for the last one, we assumed this one uses discrete type spaces, so we could solve this optimally using the interim decomposition. However, this shows that if you use the exante decomposition, which is much simpler, you get at least 1/2, and if k gets larger, you get close to the optimal. So it shows that the exante decomposition is pretty good, even though it's much smaller, more efficient computational. So now I'm going to just mention one application outside of mechanism. So I won't talk about this in too much details because this is not related to mechanism design. So this is just one slide.
3 minutes.
What?
3 minutes.
So okay. So here is the problem definition. Let's say you have m items that arrive online, and you want to assign them to a bunch of bins, and each item has a size value which depends on the bin. But the size of an item is only drawn after it's placed in a bin. And you want to maximize the total value of the assignment. So here is an example of something that fits in this framework. Let's say there is a sequence of requests that arrive online for some resource, like each bin corresponds to a resource, and the items correspond to the request. And
so this is a generalization of stochastic.
Yeah, this is a generalization of a stochastic general assignment problem. So a stochastic nested, you have one knapsack. Here you can have multiple knapsacks. And basically we show that you can obtain this fraction of the optimal offline, but using an online algorithm, and where k, assuming that the size of each item is no more than 1/k of the size of each bin. So for example, another example of this could be job scheduling, where the jobs arrive online and you have to schedule them, and you don't know exactly, but like the demand will be the resource that the job demands. We don't know it exactly until you schedule it, but you know the distribution in advance. It's based on a generalization of the magician's problem. Okay, so the part 2 is prior free mechanism design. Again, this is my proposal, and I will just give an overview, so it's not in detail. So it's competitive equilibrium matching markets. And it's a joint work with Kamal Jain and Azhar Malikian. Okay, so let's say you have a matching market, you have basically a matching problem, and the agents do not have quasi-linear utilities, which means their utility is not of this form. This is just some arbitrary decreasing function of the price. So, and you want to compute a socially optimal outcome, but you cannot use the BCG mechanism because it requires quasi-linear utilities. So here, instead, we consider a competitive equilibrium, which is defined as follows. Basically, it consists of a stable prices and stable allocation. So, which is basically an assignment of prices to items, like for example, this assignment, along with an allocation, such that every agent receives her preferred item at the given prices. Like nobody wants to get something else at those prices. So here are some prior work on this problem. So like most of these have shown the existence of a stable, basically a competitive equilibrium in this market, but the proof are not non-constructive, and there was no characterization, like no algorithm for finding the equilibrium exactly, except for like using, I mean, they all use fixed point theorems. And our contribution is an inductive characterization of equilibrium, which also is a constructive proof of its existence. And we also consider properties of highest and lowest equilibrium, and there is an application to add options, which I won't explain. Okay, so here is a definition of the equilibrium lattice. If you have two price vectors that are stable, basically stable means if you assign those prices, there is each item is, there is a way to allocate items to agents such that everyone is happy, everyone receives their preferred one. So if you have two stable price vectors, if you take the maximum of all the prices, or if you take the minimum of them, those are also stable price vectors, which means that there is a unique highest stable and there is a unique lowest stable price vector. And the same thing holds for utilities, because you can compute a vector of utilities and then compute the maximum. Like you can define a stable utility vector if there is a set of prices that induces that utility vector and so on. So here is a characterization of the equilibrium. If you want to compute the utility of an agent, this is the characterization that we come up with. If you want to compute the utility of an agent in the lowest equilibrium, the one which has the lowest prices, basically what you can do is that you can remove these agents from the market and then compute the equilibrium with the highest prices for the rest of the market. Well, the one which has the highest prices has the lowest utility for the remaining agents. And now you just offer those prices to this agent that you removed, and you see which one he prefers, and then just allocate that item to this agent at the given price. And you can repeat this for any of the agents. And similarly, if you wanted, for example, after removing this agent, if you wanted to compute the highest prices of the items in the remaining market in the equilibrium, you just take one item, for example, that's IBM laptop. You just take it out of the market, and you compute the lowest price equilibrium in the rest of the market, which gives the highest utility to these agents. And then you bring that item back to the market, and then you ask these agents if their utilities were fixed at what you computed in the previous step, what would be the highest price they would be willing to pay for that item if they wanted to obtain the same utility. And you take the maximum among those prices, and that is going to be the price of that item. And basically, you can also do this the opposite way. Like if you wanted to compute utilities in the highest equilibrium.
Does that involve adding a sort of duplicate on it? Or
no, basically. Oh, sorry. This is actually like a. What do you mean by duplicate?
You go through the thought experiment. What if there were a second item J in addition to the first item J?
Oh, you mean if you have multiple units of an item? I'm not sure what.
Yeah, but the reason I'm asking is simply that condition that you have in the bottom line there sounds a lot like a condition in Gould and Sticchetti.
Well, yeah, but they use basically they meet the linear quasi-linearity of utilities to prove their result.
Right.
Like the result is heavily.
Right, but all I mean is, but there are other results. I think is that you get the highest price, I think, by subtracting a unit, and you get the lowest price by adding a duplicate unit.
Yeah, I think that.
So that's why I'm asking if that holds here too.
Well,
The Gould negative is, I think, for quasi-linear, but when you have multiple items, you make it like...
Yeah, so basically you're asking if you duplicate all the items, right?
No, just one item. I mean, you do it one at a time.
Yeah.
And that gives the price for that item.
Yeah, I guess that's...
My recollection of the Gould-Sticchetti result was just the same as this.
Can you repeat your question?
I just said my recollection of the Gould-Sticchetti result was it's the same as this. It's you remove a player or remove an item.
Yeah, but it is for quasi.
And not.
Yeah, but they
and not adding an
this
item.
thing that if they have like they added duplicate of an item.
Yeah, they have the replicate economy, but
Remember they duplicate all the items. I don't remember.
No, one at a time.
One at
Think about it. It wouldn't make sense otherwise.
But, yeah.
It was the one that has the replicate economy. You were replicating the economy, and then you were running this modified version of the VCG thing. But it is for the quasi-linear setting, and I think we couldn't extend it to more than one.
So the point is this: the proof of global security heavily relies on quasi-linearity of utilities. So the proof that we use here is totally different. Like you cannot extend any of those. Like if you have quasi-linear utilities, you could just compute complete optimal allocation with a linear program, and the dwells of the linear program would correspond to the prices, to the stable prices. And we just, the proof would be much easier. It's very obvious. But if you have non-quasi-linear utilities, you can't use like linear programming. And basically, our proofs are based on induction, but it's like 3-4 different theorems that call each one calls the next one, and then the last one calls the first one on a market with a strictly smaller size. So the induction goes through, but it's not an obvious proof. Okay. And also, we show that the lowest equilibrium, the one with the lowest prices group strategy, which means no group of agents could gain by lying. So to conclude, for Bayesian mechanism design, we present the framework for multi to single agent reduction based on interim allocation decomposition or ex ante allocation decomposition. The decomposition basis of interim allocation would give an optimal mechanism, but it's not very practical. On the other hand, using ex ante allocation, we get approximately optimal mechanism, but it's more practical. And another implication of this is that the approximation factor only depends on the maximum demand of a single agent to the total supply. It's not dependent on the size, on the number of the agents, which suggests that the size of the market should be somehow, like, the important parameter that specifies the size of the market is the size of the maximum demand of a single agent to the supply, and not the number of agents. And we also considered some applications outside mechanism design. For prior free mechanisms, we considered competitive equilibrium matching markets and gave an inductive characterization of equilibria, and we also studied other properties, which I didn't talk about here, and we also gave application of these two adoptions. Okay, so that was the end of my
Question? Unless some people that are hungry. I'm hungry. So there are no questions. The committee will continue its questioning. So,
we should leave or not?
Pardon?
We should leave or not?
So I compressed phase 2.
No questions.
Thank you.
I'm sorry, what's going on?
What did you say?
What? What's going on now?
Okay, so we ask the audience to leave. I can rotate the laptop so that they can hear you.
I think I should leave as well. I think
I can actually stop the broadcast as well. Right.
Okay,
Well, so we want to keep hearing Jason, right?
No,
And he wants to
just
get
the broadcast.